Hey, it's Mr. Allred, and we are still talking about exponents and radicals or roots. And here we are, we're going to talk about rationalizing radicals. Reason we do this is it's generally a principle that we do not leave a radical or a root in the denominator of a fraction. There's other reasons later on you should know how to rationalize and different methods of rationalizing. But the main thing we learn here is rationalizing the denominator of a fraction. And what that means is removing the radical from the denominator. Now, that doesn't mean we erase it or just mark it out, but we're going to go through a process that, as I have here, will change the appearance but not the value. So in the same way that you could say that 1/2 equals 2/4, they look different, but they are numerically the same. So we'll change the appearance, but not the actual value. And down here in the process, to rationalize a denominator, we multiply the top and bottom of the fraction by a term that will complete the root and eliminate it from the denominator. So that means that if you think about a square root, and how we reduce those and pulled things out, where we looked for pairs of items. If we have a root and it's in simplest form, then it must not have a pair, so we're going to try and make that pair. So let's see some examples. So here we have a couple that we're going to work through, rationalize the denominator. We have the fraction 1/√2. So I'm going to multiply it by a fraction, and it needs to be the same on the top and bottom. So if we look at this and think about it, we're trying to get rid of the square root in the bottom, and right now it's √2. So there's a single 2 under there. So if we multiplied it by another √2, it would be the square root of 4, or 2 times 2 on the bottom, which would look like 2. So we created, since it's a square root, we needed 2 of them to be able to pull out, so that becomes 2 times 2, so it knocks it out at the bottom, at least the root. So if we do that to the bottom and we don't want to change the value, we need to multiply by the square root on top. And 1 times √2 is √2. So as we see there, we get something that looks like √2/2. Now, I'm not going to say that looks better, but this is a rationalized denominator, and it has a purpose. The second one here, the fraction with 5 in the numerator, and on the bottom, the denominator is square root of 6x. So again, with this right here, we need to complete the bottom. There's a single 6, we need another one. There's a single x, so we need another one. So we'll have 2 6's and 2 x's. And if we look at that, we would have something on the bottom that looks like 36x squared. And what we should realize when we pull that out is square root of 36 is 6. And I believe we talked about the square root of x squared should be the absolute value of x, just to make sure that whatever you plug in comes back a positive and can be taken a square root of. But on the top, we have to multiply by the same thing, and there's nothing that can really clean up there. So we get 5 square roots of 6x on top, and on bottom 6 times the absolute value of x. The last one here is a little bit trickier. It is 6/4 root of x. So the 4th root of x has a single x under it, but we need to do something that will complete it. And if it's a 4th root, we would need 4 x's under there. So it needs to be the same root, so we're going to multiply by the 4th root. Let me clean that up a little bit. Trying to anyway. So we're going to multiply by the 4th root. But we've only got a single x, so we need 3 more. So the 4th root of x cubed. And we can do that on top and bottom. So when I pull that over, on the bottom I have the 4th root of x to the 4th, which again will be just x when we pull it out, but we'll write it as the absolute value of x just in case. Up top, nothing is really going to combine, so I'll pull over 6 times the 4th root of x cubed, and there's no simplifying there. So 6 times the 4th root of x cubed all over the absolute value of x. Okay, so it's not just multiplying by what's there, because if this is a 4th root, it doesn't mean that we will get back enough to pull everything out. So we took the 4th root of x to the 4th. So when we did that, we said we had a 4th root and there were 4 items. This is a division. So it went in one time, which we put on the outside. That would be our x to the 1st. And our remainder was 0, which was the inside. So think back to that. So that is x to the 1st on the outside and no x's under the root. All right, so here's a few more examples. Rationalize the following. So we have the square root of 5 over 2 square roots of 3. Now, you could multiply the bottom by 2 square roots of 3, but the 2 does not have a root, so really you only need to multiply by the square root of 3. So we'll do that on top and bottom. Up top, we will have the square root of 15, and nothing will come out of there. On the bottom, we will have 2 times the square root of 9, which 2 times the square root, well, square root of 9 is 3, so 2 times the square root of 3 would be 6. So we'll have square root of 15 over 6. The next one is a little bit trickier. It's 4 over 2 plus the square root of 7. Depending on where we are, we may or may not have talked about the multiplication process here. But what we need to do is we need to multiply the bottom so that the square root will cancel out. And while we have 2 plus the root, we can multiply by 2 minus the root. This is called a conjugate. We'll see it used quite a bit in different places. But what it does, if you're not familiar with it, it creates a difference of squares. So if you are comfortable doing FOIL, what we have here is a binomial times a binomial. So the first term on the denominator would be 2 times 2 is 4. The second term would be the outer. That would be minus 2 square roots of 7. The inner term, so there's the outer, there's the inner, would be plus 2 square roots of 7. Ooh, I don't know why I wrote 6. 2 square roots of 7. And then the last one will be minus square root of 49, which will be 7. So on the bottom, when I look at this, I have a negative 2 square roots of 7 and a positive 2 square roots of 7. They cancel out. I have a 4 minus 7. So on the bottom, right now I have a negative 3. Up top, I can't do a whole lot, but I can distribute this 4 times the 2 minus square root of 7, so it'll look like 8 minus 4 square roots of 7, and there's not a lot I can do with that. So I'll bring it over. I could even see bringing that negative 3 up and making it negative 8 plus 4 square roots of 7 over a positive 3. Let me try and clean that up a little bit. The eraser is not doing so well, but it's getting there. Alright, the last example here is 8 over the cube root of 4x squared. And remember that 4 is 2 times 2. Something happened with some lag there. So 4 is 2 times 2. And I've got a cube root, so I need to complete that. So I've got 2 2's, so I need an extra 2. And I have 2 x's, so I need an extra x for a third x. So I'm going to multiply the cube by the cube root of 2x. So I'm going to do that on the top as well. So up top I'll have 8 times the cube root of 2x. On the bottom I'll have the cube root of 8x x cubed, which if you remember 8 is 2 times 2 times 2, so it's 3 of them. So that makes 2x on the bottom. Up top we said 8 times the cube root of 2x. And one thing I can do is this 8 over 2 will reduce. I'll have 4 cube roots of 2x all over x. And there will be no denominators with roots in them in these examples.